In our group, we are interested in quantum communication. That is, we want to transmit quantum information from a sender, usually labeled Alice, over a quantum channel to a receiver named Bob. This process is very interesting, firstly from a fundamental point of view, but it has also many applications, the most prominent one being quantum cryptography. And the challenge in these quantum communication protocols resides in the state transmission from the sender to the receiver. In most cases, this is performed over an optical fiber, like this one here. And the challenge with these optical fibers is, firstly, the intrinsic losses, and secondly, the fact that these fibers can only carry a finite amount of energy. If we push too much energy through our optical fiber, the intrinsic nonlinear optical effects will just destroy the quantum properties of our states. So the challenge is to develop quantum communication protocols which are both energy efficient and loss resilient. That's a formidable problem, and in order to tackle this, our group teamed up with Cosmo Lupo from the University of Cameroon. So in our case, we regard quantum communication in the continuous variation. That is, we consider the distribution of EPR states to Alice and Bob. Once Alice and Bob have received these EPR states, they can use them to perform quantum teleportation, which permits them to teleport quantum information from the sender to the receiver. The first thing we did is to calculate the quantum channel capacities of this simple setup. So on the x-axis, we have plotted the energy of our EPR state, and on the y-axis, the achievable quantum communication rates. And for this simple protocol, we see a logarithmic growth with energy. This is very bad because this tells us that we will never be able to achieve high quantum communication rates. However, we can do much better. Well, the problem here is that EPR states need an exponentially rising amount of energy to create more and more entanglement. The solution for this problem is to not use a single EPR state, but to encode the information on many EPR states simultaneously. So instead of transmitting one EPR state, we use 1, 2, 3 EPR states, which are all transmitted to Alice and Bob. And if we now use exactly the right amount of EPR states, what we obtain is a linear scaling with energy. And this is great because what we can do is that we switch from the standard logarithmic scaling to linear behavior with energy. So in fact, what we obtain here is an exponential increase in the quantum communication rate. If this got you interested, please have a look at our paper where we give all the necessary calculations and also consider the effects of loss. Thank you.